Clark, Director of Autonomous Driving and Safety Technology. My team and I have put together a series of small webinars that will discuss various materials used to build electronic hardware, the hardware that supports advanced safety systems. Throughout the series, we'll look at designs from a perspective of printed circuit board, assembly materials, and materials used to enhance some semiconductor packages and IC substrate designs. I invite you to think of the parts of these builds and how they affect the whole. I look forward to continuing this discussion with you. Throughout the journey, I'll simply be your tour guide. I'll show you some cool things from a materials perspective, but ultimately you know your designs. You understand the challenges associated to them and the final product expectations. You will choose the appropriate materials to deliver success in your products. But to help you along the way, to help you on your path to achieving the next level of autonomy, I'll supply some technical information which focuses on form factor, performance, and reliability. We've all seen car commercials that talk about lane departure warning and forward collision avoidance, but what exactly does that mean to the consumer? And what does it mean for the direction of the car industry? What is advanced driver assistance systems? As we progress through the webinars, it will become more evident that advanced safety and the path to autonomy is really a concert of multiple systems. They connect together to give the driver, and then ultimately the car itself, information to make more informed responses to the vehicle's surroundings. All of the systems are electronic, and they require some pretty sophisticated technology to create this functioning hardware. But the decision-making is the responsibility of sophisticated software. That's actually outside the scope of my organization, so instead, we'll explore the basics of how the hardware works and offer material choices that will enhance those systems. One of my favorite car commercials today states that your most advanced technology is in your driveway. And it might not be true for all of us, but the industry is definitely on the path to making that a reality. It's a testament to the fact that the vision for the vehicle is to be a complete departure from the machine that we know today. It's actually something we'll build our lifestyles around, and that's regardless of age or physical ability. So to make this happen, the automotive industry has to adopt technology from both the consumer and aerospace markets. And this is challenging for automotive because historically this market was considered very conservative. Design changes took years, and adoption of new technology was very slow to happen. Essentially, the automotive industry had to prove reliability on a product that was expected to last more than 15 years. So now car makers are trying to achieve desired safety and autonomy. They have to make new designs and they have to adopt them quickly. And then they have to prove the function of these and the performance of these designs in a much shorter time frame than they did before. So this is where I and my experienced organization come in. I personally have over 2 decades of experience in the electronics industry, and I work for a company that's supplied into electronics for over 60 years. We're also a major supplier into the automotive space. We understand the importance of reliability, and we understand the burdens put onto it through harsh conditions. So I'll take what I've learned from other market segments and apply it directly to automotive where possible. And of course, I'll offer improvements where it's deemed necessary. The concept of autonomous driving is really an interesting one, and it's filled with varying personal conflict, not to mention the huge amount of advanced electronics that we're considering. The Society of Automotive Engineers describes the path to a completely self-driving vehicle in levels 0 to 5. But essentially, what we're talking about is a supercomputer on wheels, one that will enable a car to drive itself. Today, we find ourselves already on this path. All new vehicles offer some level of increased safety, and some of the higher-end vehicles have the ability to intervene with the driver to create a safer outcome. So in addition to the technology that needs to be considered, there's also the consideration of personal comfort. How comfortable are you with turning your safety over to a machine? And we have these different types of adopters. The tech-savvy passenger trusts the technology and really can't wait for it to be introduced. Status-oriented trendsetters, they like to brag about the lifestyle. My car can do this or that. Open-minded co-pilot, that's where I find myself. I acknowledge the advantages in technology and I look forward to testing it. Safety reluctant, just as it says. These are people that are reluctant or hesitant to try a new car. And then suspicious self-driver. These are the people who prefer to keep things exactly the way they are. So you have all these different personalities. At the end of the day, the car makers need to convince the occupants through consistency and reliability. And that's what I hope to offer you. By discussing new material choices, we will enhance the consistency of the designs and the reliability of them. So as I mentioned before, these systems, they'll only progress in quantity and function to ultimately allow this self-driving vehicle. But before we can get to this end, the car makers and their supply chains are taking steps to first improve safety in a vehicle and teach the systems how to react appropriately when faced with difficult scenarios. The car makers likely see today the period of time that we're in right now as a major learning phase. Fortunately for us, the consumers, things are getting safer, but there's a long path to this end product of a self-driving vehicle, and there's a lot to learn about the function of the electronics and then how those systems work together to produce the correct outcome. So again, we look at these systems, we call it sensor fusion. That's taking information from different sensors, bringing it to a central computer, processing that information, and then making a decision on what the car will do next. This includes cameras, radar, LiDAR, and a very advanced positioning software, a much more advanced GPS than what we're used to today, and then all types of connectivity, being able to connect the occupants with electronics inside the vehicle, being able to connect vehicles to other vehicles and vehicles to infrastructure such as buildings and traffic signals. So to support these life-critical safety applications, the electronics will be influenced. Miniaturization is unavoidable. This happens for two reasons. One is there's a massive increase in electrical content in the vehicle. We're putting more systems in, we have to put them in the same amount of space, maybe in some cases even a smaller space. There's also the need for increased processing power and speed. As I mentioned, we're making critical decisions in a fraction of a second. So the processing power of these components is much faster than those historically used in automotive. Speed is a necessity. The next thing is enhanced reliability. These systems need to function longer than their consumer counterparts and in much more aggressive environments. I believe this to be the biggest challenge in the automotive space, and we'll discuss this in more detail in the subsequent webinars. And then finally, we look at unique substrates. Basically, this is the necessity to build electronics on unique materials. This can either be for specific performance properties like radar, or to save space on existing materials, putting electronic on it and a mechanical part. In the industry, we call this mechatronic. It becomes critical that the vehicle itself understands its surroundings. And as I mentioned before, this is a network of sensors. So if we look at this chart here, which describes level 2 to level 4 or level 5, we start at automatic emergency braking and forward collision warning. The workload of these systems is carried by radar sensors and cameras. These two are the largest growth segments in ADAS. Both have been critical in advancing automation and creating safer vehicles, but you can see from the chart at level 2, we're working with about 3 radar modules and 1 camera. As we approach level 4, level 5, the number of radar modules increases to 10 and the number of cameras increases to 8 or more. We know that today the Tesla Model 3 has 9 cameras. So as we progress through this series of webinars, I'll deliver an insight into what impact the electronic trends and proper material choices have on form factor, performance, and reliability. There will be a focus towards camera and radar designs, but I'll take time to explain how this changes or materials can benefit in other systems, as really the electronic trends are universal. To make advances in your technology, you need advanced materials that match your expectations. We take a holistic view at these systems. We look at them from the printed circuit board, the joining materials of assembly, and finally materials to enhance the semiconductor packaging. We have over 60 years of experience in electronics, and we pull that knowledge from all market segments. We specialize in advanced material development, and we have a complete understanding of the expectations of the automotive market. We focus on harsh environments. So that gives you an introduction into our ADAS initiative. In our next series, we'll discuss 77 gigahertz radar designs, and more specifically, some of the printed circuit board surface finishes that are used on those designs. I thank you so much for joining me, and I really look forward to continuing the discussion with you.